So that now we have know about vectors. Now let's talk about motions in higher dimensions. And so we'll first talk about the position of an object. So previously we only used the value x to define the position of an object, but well, in for example 3D, that in 3D coordinates, then the object will be defined with three numbers, which are of course x, y, and z. And by the way, this is called the Cartesian coordinate system. And for right now, we will only work with this coordinate system. You can have other systems like the polar or the spherical system, but um, this won't be necessary, at least by now. So yeah, and so because you have, and so now because we have three informations to define an object, so because of that, now we, instead of a scalar like before, we use a vector to define the position of an object, which I'm putting here R, and of course it's a, and of course it equals the vector, the x component plus the y component and the z component, and it's just like what we just learned before. And so that's about position. And how about this displacement? So we will do exactly like in 1D, which we will take the position of it after a specific time. And so that's, and remember the displacement is also a vector. And if you write down all the equation like this, then you can get the displacement vector equal in which delta x is x2 minus x1, and the same goes for delta y and delta z. And yeah, these are the two first equations that you should remember. And now let's talk about velocity. So we will do exactly the same as how we did before, but now this time is the derivative of the position vector with respect to the time t, and we will also have the average velocity vector equals, whoops, the delta r over delta t. But of course, working with vectors like this all the time will be quite hard, and so we can actually take the components of the velocity vector. And so here I have the graph that shows the motion of an object. And let's say we have at the time t, and with these coordinates, then this is the velocity vector. And you should also notice that this vector is the tangent line of the graph, and was obviously because velocity is the derivative of the graph at that time. And we can take the components of this vector and Vx, right? And so now that I can write this vector as and the z component also. And as we already know the equation for r, then we can therefore Vx is the derivative of the x component with respect to t, and same goes for Vy and Vc. And that's all you need to know about velocity in higher dimensions. And lastly, we'll talk about acceleration, which is actually quite the same. So you still kind of have the equation, which is the derivative of velocity with respect to time. And we also have the components x, y, and z of the acceleration, and also the average value too, the vector here. And yeah, it's actually quite the same.